All right, thanks for being patient here. Why don't we get underway as we let the last few people come in here. All right, hyvää huomenta. Kaikki on tervetullut täällä. Bon matin, tout le monde sont bienvenus ici. Ohayou gozaimasu. Minasan daikhangai desu. Dobre utro. Всем добро пожаловать. My name is Dan Middleton, and I am a principal engineer at Intel, where I get to spend most of my day working on open source, especially what we do here at Hyperledger. And not only do I get to work on technical things here at Hyperledger, but I also get to contribute to our company's advancement of a healthy open source environment. When we work in an open source project, we want to make sure that that's a project that Intel can be proud to be a part of. And this is a value that's shared by our colleagues at IBM and Accenture and a lot of the other companies here at Hyperledger. We'll be talking a little bit about the open source process overall, but if you want to understand how to get going in open source, maybe you haven't made contributions before, or you are actually a maintainer on a project and you want some tips about how you encourage community development, my friends Tracy and Swetha will be giving a good talk tomorrow, and I encourage you to attend that. Now, what we're going to focus on here are delicious open source flavors and bringing them together. And I want you guys to understand where these ingredients come from. So if you understand the ingredients of each of these, you'll understand how these things come together and why they taste good. And then we will give you a little flavor, we'll give you a little taste of what this is like when they do come together. This will be a metaphoric taste. So if you are allergic to peanut butter, you will be safe here. If you are metaphorically allergic to metaphoric peanut butter, I think I either really want to hang out with you and understand you better or stay far away from you. We'll figure that out. So let's jump into the history of peanut butter. When you start a story, you got to figure out where the beginning is. And I thought, well, let's go to a safe period that's well in advance of anything that we need to depend on for our information. So we're going to go way back in time to before peanut butter existed, to before any sort of enterprise blockchain existed. And back in this year of 7 BC, suddenly springs into being Hyperledger. And it's good. And that's, of course, 7 years after Bitcoin. That was clear from that date, right? That was clear? OK. But, of course, Hyperledger didn't just sort of spring out of nothing. Companies like Intel have been doing research into distributed systems for ages. IBM had been working in this space. R3 delivering product already. Digital asset, same thing. So all of these companies had ingredients that were interesting individually. And we all came together to say, hey, we can deliver something that's better than any of us can deliver individually and still have ways that we can be successful in the market. And since that time, we've started out with just 1 or 2 of the projects here, and we've grown to this lush greenhouse of projects. We've got things that are very mature, like some of the ledgers up there, Fabric, Sawtooth, down to things that are in the labs where we still have our research roots. We're still growing new ideas, and sometimes those things actually leave that gestation area, and they become projects like Ursa, and where is Avalon? Right there in the center. So we don't just create projects, though. At the same time that these projects are growing, the community around them grows. And so this is just some of the member companies of Hyperledger. And then when you take into account a lot of the companies that contribute code don't actually pay for memberships, we have hundreds of companies that are around this ecosystem. This has been the fastest growing open source project at the Linux Foundation. And it's only getting bigger and growing faster. We heard about Walmart joining this morning. So we continue to get more growth in this area. But you probably already know a lot of this background because you're here at this Hyperledger conference. So let's talk about something you might know less about, this new sort of chocolate thing. So where does chocolate come from? Let's go back in time again to a strange and mysterious time known as October. Yes, back in the strange days of October, months ago, suddenly springing into being again is a new open source organization called the Confidential Compute Consortium. And like Hyperledger, this didn't actually come from nothing. We have had companies working in this space for a number of years. Intel has actually been delivering silicon in this space for several years. There's a lot of similar members from the initial creation of Hyperledger are participating here. And one of the first things that we can start to compare about the flavors of these two organizations is you'll see some different names up there. When you see Google, that's actually Google Cloud. Microsoft is Azure. And then you'll see other names like Alibaba, Huawei, Baidu. So these companies represent a stronger CSP flavor than what we see in Hyperledger. And so we can think about what does that CSP flavor impart to the architectures that are going to be coming out of this new organization. Also, a little difference is where Hyperledger started with one project, and then we started to proliferate a lot of similar projects with the intent that they diverge, maybe cross-pollinate, test out different ideas. And now we're at a point with Hyperledger where we actually probably want to start seeing some convergence. Where the CCC is starting out is some very similar projects with the explicit intent that these things converge. And what all of these three projects up here, and they don't have a handy little greenhouse logo yet, but what these three projects do, these are all SDKs over confidential compute capabilities. And you probably are trying to decide, or maybe not, whether or not you care whether or not these things converge, because we haven't talked about what the capabilities are yet. So let's figure out what kind of capabilities we're talking about with confidential computing. What is the scope of this new open source organization? If you want to come up to speed on a broader space quickly, the UN recently released this handbook on privacy-preserving computation techniques. This covers a wider area than what confidential computing entails. It covers everything from homomorphic encryption to the trusted execution environments that we're going to be focused on. I found it a surprisingly easy and quick read, so you might enjoy that on your flight home. What confidential computing focuses on specifically, though, is protecting data in use using hardware-based trusted execution environments. And data in use is kind of a new idea. So everybody's probably familiar with protecting data at rest. This means when you write something to disk, you encrypt it. Everybody should also be very familiar with protecting data in transit or data in flight. You really don't ever connect to any system on the internet anymore in clear text with a vanilla connection. You've got HTTPS, you've got a TLS connection. You're probably actually VPNing into your company at some point today, and then making a TLS connection through that tunnel, double encrypting your traffic. But when we actually go to use this data that we've encrypted in every other part of its life cycle, we're suddenly exposing it in the clear. And that is a problem, or can be a problem. You think about the whole stack that your application runs on. So this is, of course, not to scale, but you might have a VMM on there. You definitely have an OS or some flavor of something that's representing the OS. And if you think about that in terms of number of lines of code, that might be something like 1 million lines of code in between your application and the hardware. That whole expanse of code is something that we call the trusted computing base. And the best thing that you can do for your security model is to minimize all the layers underneath that you have to rely on for trust. You want to minimize your TCP. If you can compromise the operating system, and we know that that's not a terribly difficult thing for hackers to do, then they can get at the secrets that your application is using. You might also have compromised applications that can pivot into the operating system. There's a whole lot of ways that you can get at that. So the idea with a trusted execution environment, or an enclave, which is a little bit less of a mouthful for me to say, is if you can take that security critical part of your application and take it somewhere where the operating system can't get at it, or more generally, you can minimize the TCB, so it's just the CPU working with your process and the critical portion of your process. of your application. What that would look like then to anything on your system, including something that's trying to snoop the buses in between system memory and the CPU, is everything that you put inside this specialized area is encrypted. So even if the operating system gets compromised, it doesn't have any special privilege that lets it look inside that space. That area that says cache there, if you were to look into a little lower level of documentation, you'd call that the enclave page cache. And the enclave page cache is this special area that is automatically encrypted anytime data leaves it and anytime data comes into it. So long as it matches integrity checks, it'll be decrypted within that special environment. So encryption is cool, and we've never before had this way to encrypt the data while we're using it, protect the process while we're using it. But really, I think the cool thing, and you didn't hear me say that the encryption wasn't cool, but I think really the cool thing is the integrity and authenticity capabilities that are added for these new trusted execution or confidential computing environments. And to illustrate that a little bit more, I had a lot of ideas on this slide. I actually started thinning it down when we had some time before this session started, because there's too many new things that you can do with this. But here's one idea of where this becomes important. Most of us are going to do cloud-hosted applications. We don't directly control that environment. Most of us are also going to rely on applications that other people have deployed, either within their own data centers or to a cloud-hosted environment, where we can't have perfect assurance that all of those systems are patched, and even if they are patched, they can survive zero-day attacks. So what you get that is unique with an enclave is when you deploy this application, this is in a way similar to a Bitcoin transaction in that you have a signature over the contents of the code. This is not just data integrity, this is code integrity and code authenticity. So you've deployed an application, and when the CPU goes to load the application into that special enclave page cache, it's going to do a hash of that memory space, just like you would do a hash of a transaction, and it's going to check that hash against the signature that was provided with the deployment. If it has been modified even 1 bit, we know that breaks a signature check. It fails, that application doesn't get to load. But if it does get to load, what the CPU will do is, after it's checked that signature matches, it will generate for you a report that says, here is the cryptographic identity of the application that you are running, and it passes your signature check. And what's more, here are the security properties of the system that we call the TCB level. Now your application, your remote application, in an automated way can make a security policy decision. Is this a system that I want to go actually deploy secrets into? For a lot of our blockchain-related applications, that might be deploying a secret. But also, importantly, is not to just continue to think about protecting the data, but you now have an opportunity to rely on the execution that's provided. So if we need to put some private inputs into a computation, we're going to get a result, and you can get an attestation to that result. So you know that the result was created with code that you or your consortium have already vetted, and it's got this cryptographic signature around it. And the last point with this is that there's APIs over this and other capabilities like sealing that we won't be talking about. And those building blocks let you create new things that people haven't been able to create before. And so if we come back, and I put too many builds in the slide, if we come back to what the Confidential Compute Consortium is going to be working on, they have those SDK applications, which are on the right side of the slide, or those SDKs, rather. So those are these new APIs that let you build new security properties, new behaviors into especially distributed applications, and let you create new things. So what's the rest of their greenhouse going to start to build out with? Because that's just the beginning for what we do at the CCC. Well, probably the next thing that we'll see is a higher level abstraction. This is sort of a natural flow of things. You create new low-level building blocks, and then you start to find higher abstractions around them. And since we all probably do a lot of containerized applications, we're used to the idea of wrapping our application in all the dependencies that it needs so we can easily push it out to some other environment, cloud, or what have you. What will be special here is not just that you're wrapping the application in a container, but you can describe the security properties of the application in the container language. That is a whole topic in and of itself, and we're not going to get into detail about that, but I did want to give you a pointer. If you want to check out an open source project in that space, you can search for Graphing, which is hosted at that Oscar Lab GitHub group. And there are other projects in that space, so that's just to get you started in there, and that'll give you an opportunity to see what that next layer of abstraction is. And then moving further out from there, we're going to come back to what the CCC might be doing at a later date, a little later in this presentation. But let's go ahead and pack that up in a greenhouse, just so it looks a little bit more like what we're used to seeing with Hyperledger. And these are sort of predictive things. This isn't necessarily what the CCC has already agreed to do, but this gives you an idea of where this other open source organization is going. And so if we come back to our metaphor here, we now understand this chocolatey, confidentially goodness. And you're already familiar with, maybe you like the creamy blockchains or the crunchy blockchains. You get to pick either at Hyperledger. And sort of the next evolution of what's happening at Hyperledger and generally in the industry that Dave Treat mentioned in his keynote is that these systems, a lot of them aren't even necessarily technically blockchains. I think that was a good insight that R3 had initially with Corda. You can provide a lot of the functionality that people want without fitting a very narrow description of what that technology could be. So I think more generally, these are multi-party transaction systems. So now what do we finally get when we mix together the chocolate and the peanut butter here? Well, of course, we get some delicious private multi-party transactions. Delicious. Okay, so what's special there, not just private transactions, which is this sort of golden treasure that everybody has been trying to reach for in the blockchain space, but that these are multi-party, which really reflects the nature of why you would use any of these systems to begin with. And you're able to create those because of these new security properties that are being open sourced through the Confidential Computing Consortium. So how would we reach out and taste this yummy new capability? You're just going to reach out and grab it? Of course not. We can't touch anything with our hands. They're covered with disgusting germs. So what we really want here is the power of the fork. And we'll do just a little bit more history here to see why this is interesting. So I'm going to grab a few of the projects out of Hyperledger. We've got Fabric, Sawtooth, and Besu. So Fabric in past to 2.0 now. Sawtooth was where my company started a lot of its contributions in this space. And Mick, who created Sawtooth as its initial author, inventor, he got to see the community come around and mature this code to the point that it reached a production release. It went out in 1.0, and Mick said, well, hey, I'm familiar with this code. I can use this. I got a new idea. I want to use Sawtooth, but you've added a whole lot of production bells and whistles that I don't really need. So I actually want to kind of strip some of that off because I really just want to use the blockchain portion of Sawtooth for a narrow part of my new idea. So Mick grabs a fork, plucks out a chunk of Sawtooth, and now you've got a private data objects lab. So this takes place in that little lab corner of the Hyperledger greenhouse. And Mick is working away, making trusted execution work with private data objects. He's having a good time. It looks delicious. The Fabric guys look over and they say, that looks tasty. Can we have some? And what does Mick say? He says, no, this is mine. Go away. No, Mick doesn't say that. Mick's nice. But Mick couldn't stop them if he wanted to because it's open source. Anybody's welcome to go grab a fork of it. You can run a copy directly or you can start modifying it, which is usually the reason that you make a fork. So our Fabric colleagues go grab a fork of private data objects, and now we got a new lab. Fabric private chain code. And they're working away at that. And while all this is going on, there's other parts of the blockchain ecosystem that you're probably familiar with. There's the Enterprise Ethereum Alliance. And they're working away trying to create enterprise capabilities around the Ethereum code base. And they look over and they say, hey, that looks delicious. Can we have some? And once again, Mick tells them to go hit the road. No, Mick doesn't say that because Mick continues to be a nice guy. But again, they could just fork it if they wanted to. And they take this trusted computing spec that they've been working on in the EEA for a while. And they were looking for code to get going with it. And the capabilities that were already getting built into PDO, into private data objects, gave them a good start to get going. So initially, Avalon is called something else. But as it matures, as it gains some community around it, it gets promoted to be a top-level project. It gets a new name. It becomes known as Avalon. So Fabric private chain code, meanwhile, that also starts to mature, and that starts to get integrated into Fabric. Now, when you come to a conference like this, you might be thinking, hey, it's open source. All of this is public information. That's true. But you probably would have to dig to see either in Jira or in branches to see that you've got a new feature coming into Fabric. That's probably going to come out in a few months and be part of the actual mainline image of it. Avalon, like I said, promoted to a top-level project, and that's going to be a lot visible in and of itself. So there's a lot to talk about with Fabric private chain code, which is why your afternoon tomorrow, you can go to another room at 4:15, and Mick and Jeb are going to be talking about Fabric private chain code in great detail. You'll learn a lot at that. And then if you want to see what that looks like in real life, you can see Bruno and Marcus run an actual demo of it. So I think that'd be a good way for you to spend your afternoon tomorrow. And you can see in a kind of detail that's going to give you the higher level picture that you need in order to figure out, is that something that you want to be working with? You know, particularly if you're already working with Fabric. Now, Avalon has maybe a little broader audience because Avalon is blockchain neutral. It can sit as a layer 2, which is what the EEA wanted out of that capability, why they created that spec to begin with. But interestingly, it means that it's not just a layer 2 for Ethereum, it's something that you can work with Fabric. So Avalon is something that's really applicable across Hyperledger and outside of Hyperledger. And so again, on Thursday, we have a whole workshop with Avalon. And something that's always helpful for me is if I can get hands-on with something, I might not ever really need to know how to code for this thing. But by going through an exercise with it, I learn the important parts of it. And then I might continue on with that and do some hands-on work myself with it, incorporate it into my project, or I'll at least understand how somebody else might be using that. So if I see an integration point in the future, I can take advantage of it. And I also threw up this just interesting fact that it does have a very broad appeal. And that's why we had more sponsors for this project than any other project that we've seen at Hyperledger yet. So let's go ahead maybe and dive into some of the details of Avalon. So it can be a little hard to work through an architecture diagram in a setting like this. So let's start by focusing on just the orange pieces. If this was a normal blockchain application that you're familiar with, maybe something like Bitcoin, down in the lower right corner here where you've got the bright orange box, that is your transactor, that's your Bitcoin wallet. This is somebody that wants to initiate some sort of private transaction. Generally, it's any sort of workload that requires private inputs where you don't want to publicly share those, but you want to be able to get results that multiple parties can do something with. Could be financial, could be something else. So that requester is going to submit some kind of request up into a blockchain, or interestingly, maybe not even using a blockchain, and that gets routed to the other orange box up there to actually be processed in some kind of trusted execution environment. And the specification here is kind of nice because there's other potential workers here. It doesn't necessarily have to go into something that the CCC is going to be working on with a hardware protected trusted execution environment. It might go into something that's more broadly from that UN report about different cryptographic methods. That's all built into the spec there, so it's got some flexibility, it's got some longevity to it to explore different paths. But I think even better than working through more details of that diagram immediately, we could do another good open source thing, which is I can fork slides from another company. So instead of just forking code, we can grab slides. Actually, Santander offered these slides when we asked around amongst the Avalon community who's got a use case that we can share at Global Forum. And what Santander said is, well, we don't want you to share this other thing that we're working on because we think that that has some good proprietary value to us, and also this other thing and this other thing that we've been talking about discreetly. But we have a whole lot of things that we think are pretty public, and this is one of them. So this is going to be an interesting thing to walk through, but I said I'm not real great with walking through other people's slides. I make silly metaphors like chocolate and peanut butter. I don't understand banking. I'm not a banker. And so they said, we'll make it easy for you. You don't have to understand banking. You do understand that banks exist, though. I nodded politely. And that generally these banks compete. I get that. And sometimes they have to cooperate. And they have to cooperate usually around legal issues, things like AML, KYC, this sort of thing. They can benefit or they have to benefit. They have to participate. And they also tell me that banks sometimes have customers that have lots and lots of money. I told them I did not understand this, and maybe if they could give me lots and lots of money, then maybe I would. They said they would not help me that way. But I get the idea that they have account information that they need to protect, not just for the benefit of their customers, but also for their own selfish interests, that they don't want to share customer lists. They don't want to know where, they don't want the other banks to know their clientele necessarily. But again, there's this potential problem that if there's something fishy going on, they are responsible. So if they had a global view of these three accounts, for example, they might see that the same €1,000,000 is going in a circle between the same three accounts. And that triggers some sort of AML problem. But they said, we didn't have a way to solve this problem. If we adopted something like a Bitcoin model where everything is transparent, sure, we could solve this problem, but it would be at the loss of any confidentiality for our customers. And this is sort of the general problem that we've had with blockchains since their inception. Great, we all want this full transparency, and oh yeah, we also have necessary confidentiality in order to operate a business. They said we have no way to solve this problem until, of course, the magic peanut butter cup shows up. And of course, they think of this as the central place, or not the central place, but this is their mechanism where they can now provide simultaneously the confidentiality and a way of solving the main problems that would request transparency. And they don't think of it as a peanut butter cup, they think of it as something a little bit more banky, as a vault. But what goes into that vault is initially this code, this signed code that the banks have had an opportunity to review. Everybody understands the signature of that code. Everybody trusts that code. So that code gets loaded into something like an enclave page cache. It gets an attestation, which is absolutely critical for this to work. Because you probably wouldn't accept this model if that code was just loaded into some encrypted memory. You want some cryptographic token that says that code is actually running in an environment that I trust. That's the code that I trust. And so that's what that attestation gives you. Once each of these banks gets an attestation that there's an endpoint with the right code that they can trust, then they can set up a secure connection directly into that memory space, not a connection to an operating system, to a network driver, but directly into that enclave and deliver just the financial data that they're responsible for delivering, and then there's an output that comes with that. Maybe that output goes to an auditor, maybe it goes back to the bank that initiated the investigation. But there again, you trust the attestation that the code that I trusted created an output. It probably sanitized some data, so it doesn't necessarily need to give account values for data that turned out to be irrelevant to that investigation. But you have whatever evidence is required, and part of that evidence is the attestation from your enclave. And I said, hey, great slides. And they said, no, not just slides. We have written this. This runs on Avalon. They said, would you like to run the code? And I said, I am not a confident enough speaker to toggle out of PowerPoint and try to run an application during a presentation. But some screenshots would be nice. So Santander has not just sort of the back end part of this that works with Avalon, but also they've got a whole front end for it. And this is actually not super new. They have been working on this since before Avalon was properly a project. And they introduced some of this going back to DevCon in the fall. So they've continued to expand on other things that they're doing with Avalon as the Avalon capabilities continue to mature. So if we come back to their use case for a sec, we've got all these banking participants and relying on trusted code that's in that vault, putting their secrets into that vault. So if we bring that back to the architecture picture to understand that a little bit more, your transactor, again, is in the lower right. And the secure area for, again, the code and the data is embodied by that top box. So let's dig into that just a little bit more. And something that is interesting that I alluded to earlier is that you don't necessarily even need to use a blockchain. So blockchain might be a convenient way to advertise the availability of trusted workers, to have a good place to submit work and to retrieve receipts of completed work. All that would go in encrypted form onto a blockchain. But you might not have a big enough network that mandates a blockchain. You might have a use case that doesn't mandate a blockchain. And so you can go directly into a different listener, which is the bottom box there. Either way, about half the job that Avalon is doing is orchestration. This is orchestration of trusted execution environments. So if we think back to what the roadmap might start to look like out in this other open source organization, we start out with some base building blocks with these SDKs. We create a higher level way to make use of those building blocks with some containerized solutions. And then we might start looking at, well, how do you orchestrate these environments? And probably the closest thing that I can point you to right now for what that might look like is looking at the Avalon code base. We're looking at the documentation that rises up around Avalon. All right, so we've gotten to see our delicious chocolatey confidential goodness and our different flavors of creamy or crunchy stuff getting mixed together with it. And what that leaves us with is a whole new way of doing execution with multiple parties for private transactions, whether it's in a blockchain environment or not a blockchain environment. And you've got a good opportunity while you're here. You can always go out online and read documentation. It's open source. It's always going to be there. We've got chat channels. We've got mail lists. So once you leave here, you're not blocked in any way from engaging to find out more with the actual people developing it. But your opportunity here at Global Forum is to get it sort of straight from the horses' mouths. So I encourage you to go see my fellow horses here later today. And I think we might have 1 or 2 minutes for quick questions. And then I also, for anybody who seriously doesn't have a peanut allergy or anything, I've got some peanut butter cups to pay you for your nice attention during this presentation. All right, so if anybody, yeah.
So how is any of this going to change if Intel moves over to the total memory encryption stuff?
Great question. So there is, for people who aren't familiar with this, one of the reasons that you see a lot of the cloud parties participating in the CCC is that when you've got these workloads that are on the same physical platform, they ideally should know that they're on the same physical platform, but you might have different customers using the same hardware. And the CSPs more and more want to provide some better isolation than just what a VMM can provide. And so providing encryption around each of those containers is important for security there. What you get with the TEs over and above that is the attestation and the minimization of your TCB. So if you've encrypted the entire VM, that might include an operating system in it, and you're still going to be susceptible to, if something penetrates into that space, it can still pivot around once it's inside the operating system. So Intel doesn't have any plans to get rid of these finer grained capabilities as the ecosystem moves to coarser grained ones. So you kind of get to have your cake and eat it too, which is nice.
That's sort of what I was getting at. Are they going to exist side by side, or is one going to subsume the other?
Exactly, yeah. They are going to be complementary. And so you can kind of be able to mix and match the capabilities that you need.
Can I ask one more small question?
Please.
You gave this example that said, okay, they have this thing set up, and you have the code tested, and you said all three parties put data directly into the enclave. How does that practically work? You said it doesn't go through some other interface, you're not submitting it to any guy, you're putting it directly into the enclave.
Yeah.
In a practical purpose, in a practical situation, how does one do that?
So there's two different ways to do it. One is the sort of the most asynchronous way to do it is that when the enclave is created, that enclave self-generates a key. That key only exists for the runtime of that enclave. If you kill the enclave, the key goes away, it creates a new one. So when the enclave advertises itself, maybe it's advertising itself in one of those registries on the blockchain, it advertises its public key. So the asynchronous way is you're going to encrypt your data or your workload using that public key. So the data comes over encrypted into the enclave, and the enclave decrypts it. The synchronous way to do that is that within the enclave, it's got a small SSL stack in there, and that can directly create a TLS connection in between two endpoints. So there's a couple ways to do that. Really good question.
So essentially, you would actually open a port that goes directly to the enclave.
Yeah. And so some of those container technologies that I alluded to is sort of the next wave of what happens at the CCC. What those let you do is you can describe in the container manifest, I need a trusted port, and then that will map directly into the enclave that sits over that container. All right, good questions. Yes, sir. Another good question. So a lot of that is going to be policy-based. Let me see. If I get back to the, could have stopped at the first architecture version, first slide there. But so the things that end up getting customized here, maybe this isn't actually the best slide for this, but you want your, it's always difficult to talk about distributed applications, to talk about which endpoint you're referring to. But as a relying party to something that's happening in an enclave, I want to set my own policy for what I trust. So I don't necessarily just trust that I got an attestation from an Intel CPU. That's meaningless. I need to know a priori what the identity of the enclave is, and I want to know what the signature is that I trust. So when you deploy that code has something on it called an MR enclave. No, not MR enclave. Mrs. Igner, yes. What is that? MR signer. That's the right way to say that. MR signer. So you have an identity that you've chosen as the person that publishes that code. That's where one of those identities comes from. So I trust this code. I'm the person that signs it. When I get an attestation back from the hardware, it includes that signer value, that signer identity. So that is something that's specified down at the TE SDK. But when you work with Avalon, there's going to be higher level abstraction. So here's my policy for the things that I trust. And you might want to do higher level things over and above that. Okay, well, thanks for the good questions. I think I better wind things down here for the next session, which, by the way, is also a very cool session on security topics. So if you're interested in cryptographic protocols, you can hear from some of the bright minds behind URSA that are in the back corner. And if you want some peanut butter cups, I can load you up. Thank you.